Welcome and thank you for joining me today. My name is Dilara Güçtaş and I am working as a research assistant in Istanbul University Cerrahpaşa in Chemical Engineering Department. Today I would like to present our work on the preparation of Saria-based electrolytes using polyvinyl alcohol as a template and investigation of the sintering behavior. Before we begin, I will explain my presentation plan. First of all, I'm going to talk about fuel cells and their working principles. After that, I will explain the importance of the electrolytes and, of course, sintering process and grain growth kinetics. Then I will talk about our laboratory work and how we actually produce the electrolytes. Then finally, I will tell you about our findings and results. Now, when we think about clean energy, one of the most important technology came to mind is, of course, fuel cell devices. A fuel cell produces electricity through a chemical reaction, but without combustion. It converts chemical energy from a fuel into electricity through a chemical reaction with oxygen or another oxidizing agent. And there are several different types of fuel cells under development right now. Among them, the solid oxide fuel cells draws attention with its high efficiencies up to 60%. They use a hard, non-porous ceramic compound as electrolyte, such as yttrium-stabilized zirconium oxide. An electrolyte carries the oxygen ion between electrodes and therefore directly affects the cell performance. The most popular electrolyte material is yttrium-stabilized zirconium, but it is not the best ionic conductor for SOFCs. Saria-based materials show better conductivity, and rare earth oxides such as samarium oxide as dopant in Saria produces maximum conductivity. This is why in our work we studied on 20 mole percent samarium doped Saria materials as electrolytes. And another important parameter affecting the performance of the electrolyte is sintering process. The sintering temperature and duration directly changes the density and ionic conductivity of the electrolyte. Sintering is often thought of in stages. The initial stage involves rearrangement of the particles and initial neck formation at the contact point between each particle. Second stage is called the intermediate stage. The neck size grows, porosity decreases, and the centers of the particles move closer together. This results in shrinkage. Grain boundaries begin to move, and one particle begins to grow while adjacent grain is consumed. The third stage of sintering is called final sintering. It involves the final removal of porosity. And the classical grain growth kinetics are given by the following equations. This exponent n in the equation 1 changes according to the dominant diffusion mechanism during sintering. It was stated that if volume diffusion is dominant, n equals 3, and the grain boundary diffusion is dominant, n equals 4. And in our study, we tried to estimate this n value for our powders. Now I will try to explain our laboratory work. And studies show that polymeric materials such as cellulose, polyvinyl alcohol, and chitosan can be used as template in the production of porous materials. With templating method, it is possible to synthesize ultrafine and pure powders. To produce Saria powders, first 5% by weight PVA solution was prepared. Then stoichiometric amounts of metal nitrates, which are samarium nitrate and cerium nitrate, were dissolved in PVA solution. After that, the solution was poured into a thin film and allowed to dry at room temperature. Transparent and flexible film was achieved and calcined at 600 degrees for 6 hours. During calcination, PVA matrix burned off and pure Saria powders obtained. Powders grounded in an agar mortar and pressed into 10 millimeter diameter pellets. And these pellets sintered at 1200, 1300, and 1400 degrees for 5 minutes, 1 hour, and 6 hours each. This way, we try to understand the effects of sintering temperature and the sintering time on the product. After sintering, density measurements and XRD analysis was applied, and scanning electron microscopy images collected, and finally, mean grain sizes of the samples estimated. The thermal behavior of the thin film was examined with TGDTA. The first weight loss resulted from the removal of the moisture remaining in the film. Then around 60% of weight loss occurred, and this may be attributed to the decomposition of PVA. And no weight loss has been observed after 330 degrees, and the remaining mass can be ascribed as Saria powders. And phase structures, crystallite sizes, and lattice parameters were investigated by applying X-ray diffraction analysis. XRD diagrams of the calcined and sintered samples are given in figure. XRD patterns show that it is clear that calcined powders have reached the cerium oxide cubic structure and no peak of any other phase was found, and dopant samarium cation is fully immersed into the cerium oxide phase. And after sintering, the peaks became sharper and narrowed. That indicates there is an increase in the lattice parameters and crystallite sizes of the samples, which we can see in the table. And of course, Scherer equation was used to calculate these average crystallite sizes and lattice parameters. And sample densities after sintering were determined using the Archimedes method. The theoretical density was calculated using lattice parameters. As expected, increasing sintering temperature and time caused an increase in the sample densities. It is possible to reach the density value obtained by performing 6 hours of sintering at 1200 degrees by 5 minutes at 1300 degrees. They are nearly the same values. At the same time, it was seen that increasing the sintering time from 1 hour to 6 hours had little effect on density values. Generally, in all sintering conditions, relative densities of more than 88% were achieved for the samples. And these figures show SEM micrographs of sintered pellets at 1200 degrees. As we can see, a large number of microcracks and pores were found in the samples. Also, the grain boundaries could not be clearly determined, and the grains do not have a certain shape. As could be seen with the increasing temperature and time, particles became larger, and especially after 1 hour sintering at 1300 degrees and 1400 degrees, no observable porosity was found. And the mean grain sizes of the sintered pellets were estimated from the SEM micrographs using the linear intercept method from 3 different micrographs. The process of estimating the mean grain size of the sample sintered at 1400 degrees for 5 minutes is given in this figure. A random straight line is drawn through the micrograph. The number of grain boundaries intersecting the line are counted, as we can see in this table. And the average grain size is found by dividing the number of intersections by the actual line length. We repeated this process 3 times to reduce the standard error. And the mean grain sizes of all samples are given in this table. It has seen that the highest grain size value was reached after 6 hours of sintering at 1400 degrees. And the lowest grain size value has achieved sintering at 1200 degrees for 5 minutes. However, it can be said that the increase in grain size with time is not linear. This figure shows the dependence of mean grain sizes on the sintering temperature and time. As we can see, when the sintering time is increased from 5 minutes to 1 hour, the grain size of the samples reached almost 2 times. But when the time is increased to 6 hours, the increase in the grain size did not occur at the same rate. This situation shows that the grain growth is limited at a certain point. And the N exponent in the kinetic equation gives which mechanism is dominant during sintering. The slope of the LND-LNT plot gives the value of N over 1. It has been said that the value of N around 4 for all samples, and that indicates grain growth is dominated by grain boundary diffusion. The highly effective nature of the grain boundaries provides the driving force for sintering, and the grain boundary diffusion occurs faster than lattice diffusion, and it contributes to the densification of the material rather than grain growth. And using this N value, we also calculated the grain growth activation energy for the first time as our knowledge for our products, which is equal to 375.52 kilojoules per mole for a 6-hour sintering process. To summarize, in this study, cerium-based electrolytes prepared by using PVA templating method, and the calcination at 600 degrees yielded the cubic fluoride structure of the cerium oxide, and no other phase than cerium oxide was shown. And all prepared pellets were sintered at 1200, 1300, and 1400 degrees for 5 minutes, 1 hour and 6 hours each, and densely structured electrolytes were obtained. And linear intercept method was used to estimate the mean grain sizes of the samples, and the grain growth exponent was calculated as 4, and the grain growth activation energy was calculated for the first time as our knowledge. Thank you for listening.